Hi everyone, welcome back. Today we shall be dealing with a new topic, the multiple reference frame, or more specifically, translating reference frame. A frame of reference is actually a framework in which observations are made or in which the physical laws are formulated, as we had discussed in our first lecture. Now, in all our discussions till now, we had considered only a single reference system for the motion of a particle. Now, this single reference system which we had considered consists of a set of axes that is fixed to the surface of the earth. This corresponding fixed system is called primary inertial reference. Now, for most engineering problems on the surface of the earth, the primary inertial reference serves as the primary reference system for analyzing motion. The displacements, velocities, and accelerations determined with respect to the primary inertial reference are called as absolute. But a fixed reference system may not always be possible or convenient. Sometimes it is necessary to analyze the motion of two or more particles relative to each other. For analyzing the motion of such particles, we may need to consider the measurements with respect to a moving reference frame. For example, consider a passenger who is traveling in a train. Suppose he is walking in the train down the aisle. Now, the position and velocity that are important to him is his position and velocity with respect to the train. But he also has a position and velocity relative to the earth, which is different because the train itself is in motion. So such cases occur in dynamics where the use of a moving reference frame must be employed. Here in this case, we may attach the moving reference frame to the motion of the train. Now, when we deal with the multiple reference frames, it is very important to specify the reference frame when you are taking vector derivatives. So we shall first go to the topic vector derivatives. Now, suppose I have a vector, say A, and the components of the vector are in the three directions. The scalar components are A1, A2, and A3. Now, let epsilon 1, epsilon 2, and epsilon 3 be the corresponding unit vectors along these three directions. Now, when I take the derivative of a vector, in case of we are dealing with multiple reference frames, it is important to specify the frame of reference. So, when I take the derivative, say dA by dt, I should specify the corresponding frame of reference either here, or I can specify here. Now, so if I take the derivative of this vector here, okay, I will use it here. If I take the derivative of this vector A, I will get Now, here A1, A2 and A3 are actually the scalars. So as such, the derivative of the scalar need not have the corresponding framework f. But when I take the derivative of the unit vectors, I should specify the frame of reference. This is usually the standard representation in most of the textbooks. Now, let us consider a multiple reference frame. Say I would take here two Cartesian reference frame. Suppose the primary reference frame I determined by the capital X, Y, Z, which I can assume it to be fixed, or which I consider to be the inertial frame. Now the second one, I have a moving reference frame. Say I use small xyz. Okay, so as such I have xyz as the primary inertial frame, and say I have a moving reference frame small xyz. Now the vector A, which we had discussed earlier, can be represented in terms of both these reference frames as now I had considered the vector A along the primary inertial frame capital XYZ. Here I, J, K are the unit vectors along the primary reference frame, and the same vector I had considered in terms of the moving reference frame. So Ax dash into I dash cap plus Ay dash into J dash cap plus Az dash into K dash cap. Here I dash cap, J dash cap and K dash cap are the unit vectors along the moving reference frame. Now, if I take the derivative of the vector in both of these, say in the first primary reference frame, the derivative of the vector will be equal to dA by dt xyz, capital XYZ will be equal to here. Now, if you look at closely, this corresponding primary inertial frame of reference is fixed. So here di by dt xyz, dj by dt xyz and dk by dt xyz will all turn out to be 0, since they are not rotating and they are fixed. So this will be 0, this will be 0 and this will be 0. So as such, my derivative of the vector will turn out to dAx by dt into I cap plus dy by dt into k cap plus daz by dt into k cap. Now, the same vector I shall express in terms of the moving reference frame. Now, this is the corresponding derivative of the vector in terms of the moving reference frame. Now, here these corresponding terms di dash by dt xyz small xyz, dj dash by dt small xyz, dk dash by dt small xyz. If I rewrite these terms, I will get now if you look at the last three terms, you can see that these involve the time rate of change of unit vector. Here, here, here. This corresponding terms comes only when there is rotation of the moving reference frame with respect to the primary reference frame. However, when we deal with kinematics of particles, we shall be discussing only reference frames that translate. There will not be rotation involved. In kinematics of particles, we shall be dealing only with translating reference frames. That means there is no rotation involved. Hence, all of these terms will become 0 if there is no rotation. All of these terms will become 0 if there is no rotation involved. So as such, this my derivative of the vector with reference to the moving reference frame will have these three components. Now, if the corresponding reference frame is only translating, then dAx dash by dt will be equal to dAx by dt. Day dash by dt will be equal to day by dt, and daz dash by dt will be equal to daz by dt. The rate of change scalars is constant. This corresponding vector will be equal to dA by dt into capital X, Y, Z. So this is the most important relation we shall be studying here. Now, in case of a translating reference frame, the derivative of the vector in the primary frame will be equal to the derivative of the vector in the translating frame. Now, when I say translating reference frame, it indicates that the direction of the translating axis x, y, z always retain the same orientation relative to that of the fixed reference frame capital X, Y, Z, as shown in this figure. The orientation of the axis of the fixed reference frame and the translating reference frame need not be the same. In this figure, you can see that the fixed reference frame is not in the same orientation as the translating reference frame, but they will not rotate relative to one another. Next, we shall be dealing with the position, velocity and acceleration in the two reference frames. Now, look at the figure here, showing the position of a particle at point P with reference to the fixed and a translating reference frame. The position vector of the particle small r, which is taken with respect to the fixed reference. Capital R indicates the position of the translating frame, the small xyz, with respect to the fixed reference frame. Rho indicates the position vector of the particle with respect to the translating reference frame. Now, if you look at the vector triangle, we can see that small r vector is equal to capital R vector plus rho vector. Now, taking the time rate of change of vectors with respect to the fixed reference frame capital X, Y, Z, we have here dr by dt with respect to capital X, Y, Z is equal to d capital R by dt with respect to capital X, Y, Z plus d rho by dt with respect to the capital X, Y, Z. Now, here dr by dt with respect to capital X, Y, Z represents the velocity vector v x, y, z with reference to the fixed reference frame capital X, Y, Z. Now, dr capital R by dt x, y, z indicates the rate of change of the translating reference frame with respect to the fixed reference frame. So, I can indicate this as r dot, and d rho by dt capital X, Y, Z will be equal to d rho by dt with reference to small x, y, z, as we had discussed earlier. But d rho by dt small x, y, z indicates the velocity vector with reference to the translating frame x, y, z. So, the velocity vector with respect to the fixed reference frame x, y, z is equal to the velocity vector with respect to the translating reference frame v small x, y, z plus r dot vector, where r dot indicates the rate of change of the translating reference frame with respect to the fixed reference. So I can rewrite this as Vxyz is equal to V small xyz plus R dot. Now, similarly, we can obtain the acceleration of the particle by taking the time derivative of the velocity. Now, the acceleration with respect to the capital fixed reference frame xyz is equal to acceleration with respect to the translating reference frame small xyz plus capital R double dot vector. Now, this corresponding concept can be employed in the study of relative motion. Consider I have two particles A and B undergoing motion along their paths as shown in this figure. The absolute position of the particles may be expressed in terms of the fixed reference frame capital XYZ with the help of the position vectors RA and RB. The origin of the second frame of reference small xyz is attached to the particle A, which can translate with respect to the fixed reference. The position capital B measured relative to A is denoted as the relative position vector RB with respect to A. This also sometimes referred to as RAB. Which is now, if you look at the figure once again, you can see the vector triangle from which I can develop the relation RB vector equals RA vector plus RB with respect to A vector. Now, if I differentiate this equation with respect to time, we can get the velocity vector, which on differentiation again, which I will get the acceleration vector. So if I differentiate this, I would get which will turn out to be and which will turn out to be so here I can find the absolute position of RB in terms of RA and the relative position RB with respect to A. Similarly, I can find the absolute velocity VB and the absolute acceleration AB, all with reference to the fixed reference frame capital X, Y, Z. Now, let us do a problem here. The boat with a cruising speed, that means the speed of the boat relative to that of water, of 24 km per hour is crossing a river that has a current of 10 km per hour. Find the course determined by the angle theta that the boat must steer in order to follow a straight line from A to C. B. Find the time required for the boat to complete the crossing. This is a question from Python. Here I attach the primary reference onto the ground and the translating reference with the corresponding flow of water. Now if you look at this closely, you can see that here I will be equal to I dash and J will be equal to J dash. I will say again, the primary is attached to the ground and the translating is attached to the water. Now if you look at this closely, it is given in the question that the velocity of the boat relative to the water is given as 24 km per hour. So the magnitude of V small x y z is given as 24 km per hour. It is also given that the velocity of flow of water is 10 km per hour, which actually indicates the velocity of the translating frame with respect to the fixed frame. So I can give as R dot is equal to 10 km per hour. These are the magnitudes alone. Now let us first consider the velocity of the boat relative to water. In terms of vector format, V x y z. Now it is shown that the corresponding boat relative to water moves at an angle theta, 24 km per hour at an angle theta. So I can write this in terms of vector 24 cos theta into I cap plus 24 sin theta into j cap. Now here remember one thing, I and I dash are same, so I am representing here in terms of I and j instead of I dash and j dash. This is the first one. Now velocity of water relative to ground, which is r dot vector. Now if you see in the figure, it is shown that the flow of water is in this corresponding direction. So my vector r dot vector will be equal to minus 10 j cap. The third one is velocity of boat relative to ground, that is V capital X Y Z. Now in the question it is given that the corresponding boat travels perpendicular to the flow of water. So my V capital X Y Z will be equal to V X I cap plus 0 j cap. But Vx vector is also equal to Vxyz small vector plus r dot vector. V vector xyz is equal to 24 cos theta into I cap plus 24 sin theta into j cap minus, and r dot vector is minus 10j vector, which is equal to Vx into I cap plus 0 into j cap. Now if I relate the terms, I will get Vx, that is the corresponding boat is moving perpendicular to the flow of water. This will be equal to 24 cos theta, and the second one 0 is equal to 24 sin theta minus 10. Now solving this equation, you will get sin theta is equal to 10 by 24. Therefore theta is equal to, if you solve this corresponding equation sin inverse, you will get the answer of 24.624 degree. Now substituting this one in this equation, Vx is equal to 24 cos 24.624, which you will get the answer of 21.82 kilometer per hour. So this is the corresponding velocity of the boat with respect to the primary reference capital XYZ. Now the next part of the question is finding the time. Now the time required to cross this river will be equal to the corresponding distance, that is 4.8 kilometer divided by the velocity 21.82 kilometer per hour. So this will be equal to 0.22 hours approximately, which is equal to 13.2 minutes. So this question I had solved based on the concept of the moving reference frames. It is important that you study both the concept of moving reference frame as well as that of relative motion, so that you have a better understanding of the concepts. Now moving on to the next question. The bars OA and AB are each 400 millimeter long and rotate in the xy plane. OA has a counterclockwise angular velocity of 10 radians per second and a counterclockwise angular acceleration of 2 radians per second square. AB has a constant counterclockwise angular velocity of 5 radians per second. What is the velocity and acceleration of point B relative to the fixed point O? This question is from the textbook by Anthony Bedford. Let me draw the figure here. You have two rods OA and AB. OA is inclined at 25 degrees at an instant of time and AB is inclined at 60 degrees. Now it is given to you that the angular velocity of A with respect to O. So I am directly writing omega A is equal to 10 radians per second. The second value is the angular acceleration of A with respect to O. It is given as 2 radians per second square. Then the angular acceleration of B with angular velocity of B with respect to A. it is given to you as 5 radians per second, and RA or ROA is equal to RAB is equal to 400 millimeter or 0.4 meter. The angular acceleration of B with respect to A, it is 0 since it is undergoing a constant angular velocity 5 radians per second. Now the question is finding the corresponding acceleration and velocity of B with respect to O. Now since both these rods undergo a rotation, we can use the polar coordinates for expressing the motion parameters, which can be later converted into the Cartesian coordinate system. So let us solve it out. Now consider the motion of B relative to A. Now first we find the velocity and then the acceleration of B with respect to A. Velocity of B with respect to A can be given as RB with respect to A into omega B with respect to A. We have already studied that the velocity is equal to R omega. Now this corresponding velocity is in the direction of E theta or epsilon theta. Substituting, we get 0.4 omega B with respect to A, 5 epsilon dash theta, which is equal to 2 epsilon theta. I'll express for the time being epsilon theta dash. Okay. Now acceleration. AB with respect to A is equal to, you have RB with respect to A omega B with respect to A the whole square, this along epsilon R dash plus R B with respect to A alpha B with respect to A plus 2 R dot B with respect to A omega B with respect to A epsilon theta dash. This is the corresponding, you have here a negative sign which indicates that the corresponding value is in this direction. So this is the equation if you are finding the value using polar coordinates. Substituting, will get minus 0.4 into omega with respect to A is 5 square epsilon R dash plus RB with respect to A again 0.4 alpha B with respect to A, I think the value is alpha B with respect to A value is 0 since it is moving with constant velocity. So this is 0 plus, now this corresponding value 2 into RB with respect to A dot is also 0. So this will become 0 and omega B with respect to A, I think it is 5 epsilon theta dash. So this will, both these values will become 0. So as such you will have the corresponding value of minus 10 epsilon R dash. So velocity of B with respect to A is 2 epsilon theta dash meter per second. Acceleration of B with respect to A is minus 10 epsilon R dash meter per second square. Now these are the corresponding values in the polar coordinates. We will have to convert it into the Cartesian coordinate system so that you can relate both of these. You can relate the corresponding velocity and acceleration of B with respect to A and A with respect to B to get velocity and acceleration of B with respect to O. Conversion is required here. So first let us convert both of these two. Now you can see from this figure that epsilon R dash will be in this direction and epsilon theta dash will be in this direction. So as such, you have to express epsilon r dash and epsilon theta dash with respect to the Cartesian coordinate x and y. From this figure, it is clear that epsilon r dash is equal to cos 60 into I cap plus sin 60 into j cap, and epsilon theta dash will be equal to minus sin 60 into I cap plus cos 60 into j cap. Okay, so substituting this value in the previous equation, VB with respect to A is equal to 2 epsilon theta dash, which is equal to 2 into minus sin 60 plus cos 60 minus sin 60 I cap plus cos 60 into j cap. If you substitute this corresponding value, you will get the answer of minus 1.732 I cap plus j cap meter per second. So we have converted the corresponding value of velocity from the polar coordinates into the Cartesian coordinate system. Acceleration A B with respect to A is equal to minus 10 epsilon r dash, which is equal to minus 10 into cos 60 into I cap plus sin 60 into j cap, which on solving you will get the value of 5 I cap minus 5 I cap minus 0.866 j cap meter per second square. So here we had found out both the acceleration as well as the velocity with respect to point A in terms of the Cartesian coordinates. Now next we move on to the corresponding velocity and acceleration of A with respect to O. So motion of, next is motion of A relative to O. Now here I can write the corresponding velocity of A. Instead of writing OA, I can directly write VA equals minus RA omega A epsilon theta, where the corresponding value of epsilon theta, I can write it epsilon theta and epsilon. This will be epsilon theta, this will be epsilon r. So this will be equal to minus 0.410 epsilon theta. I can convert into the corresponding Cartesian coordinate which we had done earlier. So this will be equal to minus cos 25 I cap plus minus sin 25 I cap plus cos 25 j cap, since the corresponding angle of inclination is 25 degrees at that instant of time. So if you solve it out, you will get the corresponding answer as minus 1.69 I cap plus 3.625 j cap. Similarly, I can find out the corresponding acceleration. Now, acceleration of A will be equal to minus RA omega A whole square epsilon r plus RA alpha A plus 2 RA dot omega A epsilon theta. So substituting the value, we will get minus RA, it is 0.4, omega it is 10 square epsilon r, and then RA 0.4, alpha A I think the value is 2. So here 2 plus this corresponding value to RA dot will be equal to 0. So I can stop it out here, epsilon theta. Now if you convert epsilon r and epsilon theta, you will get minus, this will turn out to be 40 into epsilon r is cos 25 I cap plus sin 25 j cap plus 0.8 epsilon theta, it is minus sin 25 I cap plus cos 25 j cap. If you solve it out, you will get the answer. Acceleration of A equals minus 36.59 I cap minus 16.179 j cap meter per second square. So this is the corresponding value of acceleration of A with respect to O. Now our aim is finding the corresponding acceleration of B with respect to O. So here I write B with respect to O. Now velocity of B or with respect to O, or I can directly write VB itself. So VB will be equal to VA plus VB with respect to A. This is the corresponding equation of relative motion. Similarly, AB is equal to acceleration of A plus acceleration of B with respect to A. I think I forgot to write the arrow mark in the previous terms. Just remember that. Minus 1.69 I cap plus 3.625 j cap. This is the corresponding value of VA. Now VB with respect to A will be equal to minus 1.732 I cap plus j cap. So if you solve it out, you will get the answer of minus 3.422 I cap plus 4.625 j cap. So this is the answer, velocity of B with respect to O, or just VB. Similarly, we can get the acceleration of B as such. So substituting the value of acceleration of A, the answer is minus 36.59 I cap minus 16.179 j cap. Acceleration of B with respect to A will be equal to minus 5 I cap minus 0.866 j cap. So if you solve it out, you will get minus 41.59 I cap minus 24.84 j cap meter per second square. So here you can see that we had obtained the corresponding value of the velocity and acceleration in terms of the Cartesian coordinates. So in such cases where the corresponding inclination of the rods is different, then you will have to apply first the corresponding polar coordinates and then convert it into the Cartesian coordinates. So in this question, it is asked to find the value of velocity and acceleration and not the magnitude. So as such, this corresponding answer is right. There is no need of finding the magnitude as per this question. With this, we come to the end of the kinematics of particles. In the next lecture, we shall be moving on to the next unit, kinetics of particles. Thank you all.
you.